Hello and good afternoon. Now I got to begin with a shameless plug for a project that's going on in Sydney that I'm involved in. It's called New Agendas for the Study of Time Connecting the Disciplines. And in this project we set new agendas for the study of time by, well, connecting the disciplines. For more details, we have a website. You can go there and see who's working on the project, what disciplines we're connecting, concepts, and that sort of thing. But along this vein, I'm going to offer a schema today that offers a systematic means of evaluating and establishing a coherent conceptual framework for quantum gravity programs. So kind of looking at the metaphysical tools we can use as I already have for conceptual analysis and trying to apply them to physical concepts. In particular, the concept of time. Now, why should we bother? Well, if you were convinced by the first talk with Nick and Chris, I don't need to tell you why. But there's a general call, kind of captured in that talk, for philosophers to take up arms, or rather brooms, to clean up conceptual meshes in quantum gravity. So, for example, we have a quote here by Butterfield from 2001. They have a couple of papers where they look up conceptual difficulties, or they outline conceptual difficulties in quantum gravity debates. And so on this quote. Oh yeah, sorry. Project. So at the end of the quote, yet there is still no satisfactory theory. Rather, there are several competing approaches, each of which raises severe problems, both technical and conceptual. So there you go. This suggests that there's conceptual cleanup work to be done with quantum gravity, given that certain interpretations of general relativity and quantum mechanics appear to involve conflicting concepts of time and space. The examination of such concepts may help point towards a means of merging the theories. But although such authors do indicate the potential merits of examining quantum gravity in terms of its core concepts, they don't usually develop or apply a systematic means of conceptual analysis of such concepts. But we have tools in metaphysics, so I'm going to look at those and see what we can do. Can you hear me better now? Is it okay back there? All right. So here's how we're going to proceed to do so today. First, I'll look at conceptual analysis and the concept of time and quantum gravity. We'll look at a particular account that's the most developed, which is Frank Jackson's analysis, JCA, I'll abbreviate it as. We'll see a problem with it. And I'm going to set up two additional desiderata for a conceptual analysis. And I'll propose an inventively titled Alternative Conceptual Analysis, the Alternative Conceptual Analysis, or ACA. That overcomes these two problems. And finally, I'll look at a case study. We're going to look at Rovelli a little bit and his partial observables. Now, why Rovelli's quantum gravity program? And it's just going to be a tiny bit. I don't have time for the whole thing. My motivation for doing so, because I developed this conceptual analysis originally to look at timelessness in Julian Barber's theory of time. He claims that there is no time fundamentally. And so I want to see if this conceptual analysis is also applicable to other quantum gravity programs. So that's my personal motivation. But also, he says we should forget about time. What does he mean by that? What exactly is this time that we're supposed to forget about? What temporal features involved in that? And as we'll see, my brief analysis here will show that it's messier than it appears. So there's the outline, and away we go. So in this first section, I'm going to develop conceptual analysis for time across physical theories. Let's start by going down to our local grocery store. Here we are, the metaphysics aisle. Usually buy the eggs. We misspelled supervenience. So let's go to the shelf and see what we have under conceptual analysis here, shall we? There's a couple options here. You got the store brand. We don't want that. And then you have Michavek's conceptual analysis. This one isn't developed to that. That's a Honda Civic covered in meat, a Michavek. Yeah. But Frank Jackson's conceptual analysis, the Frank with Jackson. That one, I've heard good things about it. So let's see what people are saying. Here's a quote from Lawrence and Margolius. It's perhaps the most explicit and detailed account of conceptual analysis available. Hey, let's try that one. So here it is. And let's look inside. The ingredients. What's involved here? Concepts. Concept is just the terms meeting on this account. Some are complex. That means that they're composed of other concepts, so you have some sub-concepts. evolves in like concept of time. Maybe you have different temporal features like there being passage or having directionality or stuff like that. I think time's a complex concept, but I'm not going to argue for that. And also, it's a type of network theory. In network theory, a concept structure is determined by its role in a theory. And this role can be put in terms of definite description. I'll exemplify that later so you see what that is. And the concept, the reference of this concept is whatever fulfills this description. Now, it's composed of other concepts. There's different kinds of structures that you can, options for composing these concepts. This network theory is one type. There are others. Well, network theory is a type of theory. And theory, you thought my titles were inventive, right? They actually call it that. Concepts form a web in which they're interrelated, and the concept's meaning is determined by its role in the theory. Now we'll go along with Frank Jackson assume that that's the structure we should have. Just for contrast, here's some other ones. The classical theory, you have a definitional structure, and it's composed of simpler concepts that express its necessary and sufficient conditions. You know, the good old bachelor, the unmarried man, right? Necessary and sufficient conditions for that. And then you have prototype theory where you have some kind of paradigm, and that has different properties, like for bird, you have having wings, can fly, has a beak, all that good stuff. And those are the things that this concept has to have. But we're going to go with Frank Jackson's one, which is a type of network theory. The role, something it plays, the role that a concept plays in the theory is meaning. It's what it is. So, what good is this conceptual analysis? Well, Jackson uses it to solve what he calls the location problem. And this is the problem of reconciling any given phenomena with one's lower level ontology. So you have upper level claims about the world, like there is water. Oh, philosopher's favorite example, right? Water, H2O, isn't it great? And then you have lower level descriptions like there is H2O. And he wants to ask, what's the relation between the two? It's conceptual analysis that you can acquire with as to what this relation is. How do we do this? Well, there's two steps. First of all, you find out what counts as the reference of the upper level terms. And we do this by first establishing the third folk theory about water. And why is that? Because earlier we saw the concept term is the term's meaning, and the role it plays, that the concept plays in the theory. These are all the same thing. So we need that folk theory to start out with. Now, how do we go about doing that? Well, we engage in armchair analysis. We sit around and we think about water. You know, possible cases. In other words, where it's red, but it fills the lakes and streams, it's potable, and all that good stuff. Is that still water? Mm-hmm. So that's how we established a shared folk theory. And then once we have this folk theory, we can determine what role a concept plays in it. So we can determine what role water plays in it. And then this role can then be put in terms of a definite description. So in the case of water, we have this mess. Water is the stuff that fills lakes, falls in the sky, is colorless, odorless, etc., or satisfies enough of the foregoing. So here we have, whatever has most of these properties is going to be the reference of this concept. That's step one. We completed. Woo-hoo. So far, so good, huh? Oh, yeah. The second step of resolving the location problem is to determine whether statements involving the concept are entailed by lower level claims. Now, in the first step, we determine what what water refers to. Establish the reference for the terms of the upper level claims. And with step two, Jackson claims that the relation between these claims is one of entailment. The lower level claims should entail the upper level claims. Further, in JCA, if there is such entailment, then the upper level concept is accepted. If there's not such entailment, then you reject and eliminate the folk concept. Now, Jackson actually in practice does this. He eliminates them, but he claims he wants to just point out incongruities and not do that. But he applies analysis and eliminates them, so I'm just going to keep sticking with that. And then he goes through this little argument here. to show how this works. So step 1 gave us P1, water is the watery stuff of our acquaintance. We filled that out with our definite description. Premise 2 we established empirically. We got to go out and find out what that water stuff out of the world is made of. And since it's the same kind of stuff, we can identify the two. So in this case, our folk concept of water is identifiable with our lower level concept H2O. Oh, yeah, it worked out good, didn't it, huh? When we solved the location problem, we could determine whether we need that watery folk concept thing. Now before moving on to apply this as a temporal example, I want to point out an assumption I'll later return to and say it's wrong, but I'm probably preaching to the choir with this one. He claims that we get our lower level description from our best scientific theory. Scientists develop sufficient enough for us to be confident of the kinds of properties and relations that are needed to give a complete notion of non-sentient reality. They will probably be of a kind with those that appear in current science. Yeah, he assumes that we're just kind of given the bottom part. The water is H2 and all the properties it has. But come back to that in a bit. Now, let's apply this to a temporal example. So there's the big picture. This is how it works there. We have step 1 is the first line, and the rest is step 2 there. And we go back to determine whether the concept we picked out with our folk theory is inside by the bottom stuff there, by the fundamental ontology. So let's apply this to the temporal example. Just one, not plural. We're going to assume that the present is the only feature of our common sense folk time. And so for step 1, we go to our armchair and we think about our folk time. So there, I don't know if you can see that, that's like a banana boat. It's the moving now, present. There we all on it, flowing down the river. Yeah. And I'm just going to assume, I'm going to use this quote from calendar. It captures this here. It's an objective feature of the world. It's a global now shared by all. And it's different from the way, it's different from what here is like spatial relations. From this we can construct a definite description that time has all those features. So it seems to mirror the water case. We can do the same thing with the temporal case, at least with the folk concept.
Yeah. I mean, is there a motivation for this assumption that the now is the only constituent of the
just for simplicity, just for the example's sake. That's all.
So for your example, you're going to just consider the folk concept of now rather than assuming that now is the extent of the folk concept of time.
Yeah, exactly. All right, so step 2, we consult our best scientific theory to see whether anything fulfills that definite description we gave. So let's assume for fun that it's our best scientific theory is a neo-Lorentzian interpretation of special relativity. So according to that, there is absolute simultaneity and a preferred reference frame. So it looks like a folk concept has most of these features. We can go through the same thing and identify our folk concept with this neo-Lorentzian concept of time. And we move to step 2 here. Oh no, sorry. Now let's try it with a more reasonable best scientific theory. We look at the Einsteinian interpretation of relativity where it doesn't have this absolute simultaneity thing. Or a preferred frame, there's pictorial representations of the folk concept versus the Einsteinian one. And so since it doesn't tell that it has completely different features, we eliminate the folk concept. So that looks alright, I guess. So, JCA is looking good. Have we found a ready-made conceptual analysis for time? No. Well, we'll go back to the problem with JCA that I hinted at earlier. We get our lower level description from our best scientific theory. He assumes that. Now, assuming that we can just read it off our ontology and metaphysics from our theory is problematic. Wouldn't it be nice if we could? You may ignore other ontological and metaphysical options a theory might have, like even in water, you could tell the status of covalent bonds. So you have different ontological readings of that. And risk of incorporating entities or metaphysically redundant, irrelevant, or inconsistent. Since you're just reading them off, you can just have any old set. Sure, you might go back and see if they're inconsistent to try to fix them, but there's no real systematic way of doing so. So, a couple upshots. We should at least be aware of other readings, metaphysical and ontological ones that qualify our analysis. And the concepts read off a theory should not be taken for granted. Such concepts themselves are in need of analysis. So we have a little shopping list here, a list of the desiderata from Jackson's problem. First of all, we don't want our conceptual analysis to problematically read scientific concepts off the theory. And then in view of our quantum gravity targets, we want to apply this to, finally quantum gravity. We want to be applicable to more than one scientific theory, right? Because you got general relativity, quantum mechanics, potentially, all that stuff. And we also want to include an integrated analysis of folk time with the analysis of time and physical theories. That might be debatable. You could say, well, you don't need that. Just eliminate it like good old Jackson would do. But some physicists, like Julian Barber with his account of time capsules, and Rovelli arguably with his thorough time hypothesis, do incorporate some account of our experience of time when they claim to get rid of time fundamentally. So just to be coherent and consistent, I think we should look at the whole picture again.
Sorry, I guess I'm a little confused. What does it mean to say that it's applicable to more than one scientific theory? What's it?
Oh, the conceptual analysis.
But I thought they didn't apply to the scientific theories. I thought they rested on them.
No, these are, you're right. These are just desiderata. We want to actually have our conceptual analysis be applicable to concepts in scientific theories. You're right. So I pointed out before, Jackson's analysis didn't do
why?
that.
Why would we want that?
So we can figure out what's going on.
But if we think that quantum gravity is the correct theory, why would I care how it applies to general relativity or to say non-relative physics, quantum mechanics? Why would I care about any of that?
Well,
if the idea is the best theory, and I don't think there's a quantum gravity lying around to be called the best theory, but if that's the target, why would we want more than that?
Because there seems to be an issue if you take with the concepts involved in quantum gravity. It doesn't seem they're either not made explicit exactly what's going on there, or they're kind of imported from your general relativity or your quantum mechanics in some cases. And this works to track those, and whether the concepts that we import from the other theories that we're building quantum gravity out of actually are coherent.
May I make a comment maybe to see if I have understood what you are saying? I mean, when you do a new theory, it's not that you are building up, you think that it's the right theory, but it's not that you are building up something coming out of nothing. You are taking some elements of some other theories and putting them together. So you wanted to see if your concept, the concept that you are retaining, are good in one theory, but should be good also in the other theory from which you have imported them. So
I get that as a general method of scientific construction, right?
So I guess this is a way.
But we're supposed to be doing conceptual analysis of some concept, or something, and the prescription is use the best scientific theory.
Oh, that was Jackson's prescription. What I'm doing, I was trying to reject that and I'm going to move to constructing an alternative conceptual analysis that doesn't incorporate that. We don't assume that there isn't the best scientific theory that we can just read things off of. Instead, we actually have to go back and analyze concepts in that theory.
So it's not just that sorry, I don't mean to spend all your time, but it's not just that it's not possible to read off transparently concepts from the best scientific theory, but you're also maintaining further that the concept of best scientific theory is itself problematic.
Yeah, that too. Okay, thanks. So there's what we want for a conceptual analysis have these things. Give our quantum gravity target and the problem identify with Jackson's conceptual analysis. So here we go, the alternative conceptual analysis. Since our store-bought JCA didn't work out, let's create a product that fills the gap in the market we've identified. First and foremost, how to market it. Well, we'll put its creative name there, and then continue with the meat theme. Our protagonist will be a prime choice of beef. I guess it'd be engaging in a alternative sport, wolf wrestling. That's pretty alternative for a piece of steak. And for short, we're abbreviated as ACA, or what a snake might say, I went under attack by wolves. ACA. So, here's how you use ACA. First of all, you start off, it's going to come in two steps too. Step one is you obtain the theories being examined. So you could have your folk theory there, physical theory, maybe quantum mechanics, and kind of general relativity. And for the folk theory, you consult intuitions about possible cases, just as we did in Jackson's conceptual analysis, so I've spelled it out here. And then for the scientific ones, we consult interpretation of the theory. For multiple theories, which we seem to have in quantum gravity, we want to treat them as parts of a single network. And I suggest we do this by underpinning them by certain metaphysical and ontological principles or commitments. Note that the theories might lack connections at this stuff, but they might likely be made apparent and developed over the course of the analysis. Now in step 2, we determine what role time plays in the network. First, we preliminarily identify this role through the surface readings. We still have to use surface readings. You have to identify it initially somehow. But we move on. We go beyond that, and we determine whether the temporal roles clash are redundant or irrelevant. And there's some options there. If they aren't, then you can say that there is time. If they do clash or redundant or irrelevant, you can just give up and say, oh, I'm not so that. Or you can attempt to salvage time engage in metaphysics. This is the Jacksonian thing. Where you just you have a list of ontological commitments. You want to make these as consistent, as coherent as possible. And so with this too, as you go down to the green option there, you have sort of a feedback loop where you go back into this and try to, rejig stuff, the formulations and the theory itself, and you can also rejig the concepts of time and maybe armchair intuitions and interpretation. So it's not just one directional. If you go with that, it's sort of feedback that's going on. Alright, so we resolved, we fulfilled these desiderata things. We don't problematically read scientific concepts of theory. We have to do somehow to initially identify them, but then we go back through. We just accept whatever we read as it is. And it's applicable to more than one scientific theory with this principle underpin network thing. And finally, we include and integrate an analysis of folk time with the analysis of time physical theory, by considering parts of a single network. All right, so there we have it. A conceptual analysis that is designed to be applicable to time across physical theory. Did you have a question?
Yeah, just to understand if I understood, how crucial it is that you can put them in the same network. I mean, there may be physical theories that do not share an ontology, for example. And so you cannot really select the common ontological principles to regard them as part of the same network.
Yeah.
Can you extend the construction to these cases, or?
Well, see, it works for Julian Barber's account because he's explicit Leibnizian one, so that's nice. And Rovelli actually has Cartesian and Aristotelian, as I'll come here shortly to, principles underpinning his accounts. But whether it works for other accounts, that aren't based on things like that, you could probably dig some out or have some set that you want to aim at or try to incorporate maybe some sort of relationalism or something, if you like that stance, and then go through and see if you can have a coherent account of that. But yeah, it'd be kind of tricky in those cases. There's lots more moving parts that you could have. Okay. Applications of Rovelli. So, here's a pictorial representation of Rovelli with his slogan, forget about time. Now, as sketched in the previous section, ACA requires to import the entire network of theories and chart the roles of time in it. Clearly, they don't have time to do all of that now for all of Rovelli's quantum gravity program. Instead, I'm just going to look at it as partial observable, which kind of underpins the account. And after I show very quickly what role this element plays in this program, we're just going to poke around a bit with ACA to see if we find anything weird. Not like that. More like presupposed temporal concepts lurking about. So what does he mean by this forget about time? What are we supposed to forget about exactly? That's what I'm going to try to show us. Kind of messy. Like aliens and raviolis, so this can be messy. All right, so the strategy for merging his strategy for merging general relativity and quantum mechanics goes like this very quickly. He says, I have to do this just to illustrate the role of partial observables in this account to show that they are sort of a fundamental-ish thing. So he claims, first of all, that space-time is the dynamical field, is the gravitational field. And he takes this to be a lesson from general relativity, that it must be incorporated into a quantum gravitational account. He reasons that the manifold has no physical content because of active diffeomorphism invariance. He takes general relativity to describe the world as a set of interacting fields. And then you have two there, quantum mechanics, he claims, tells us that every dynamical field has quantum properties, so space-time itself, which is just a dynamical field, must exhibit quantum properties. So these properties must be represented in quantum mechanical terms. Now, given a strategy for combining quantum mechanics and general relativity, and as we'll see, certain relational principles he holds, he seeks to eliminate temporal features that distinguish the time variable from other variables. It is his partial observables that are supposed to accomplish this task, to show that the roles that the time variable plays in general relativity and quantum mechanics aren't incompatible. He explicitly utilizes partial observables in a non-relativistic formulation, general relativistic formulation, and quantum mechanical formulation and interpretation. So these partial observables play some sort of role in each of these accounts he gives. Notably, he seeks to undercut a proposed privileged time and quantum mechanics concepts. For example, in conventional quantum mechanics, observables occur at a fixed time, and states considered to be instantaneous, so he wants to redefine observables and states so it's not rely on some kind of special notion of time. And in doing so, he wants to show that time is on an equal footing, he says. It's on an equal footing, he says this repeatedly, with other variables, and thus eliminates temporal features that distinguish time's role as a constant independent parameter, for example, from that of other variables. So I'm going to apply ACA to see whether Rovelli's time variable is actually on equal footing with other variables. To do so, I first have to look at the principles that underpin its account. With the network, with the analysis I'm proposing, it's these ones that underpin the entire network. They're crucial for the analysis. Yeah. So here's some ontological principles. Now, he explicitly commits himself to ont S, but the temporal ones, he pulls the first three out of Descartes and Aristotle, and he doesn't give explicit formulations of the temporal ones. He claims whatever his are, which he doesn't pin down exactly, are novel. But actually, there's been research done recently to suggest that Descartes actually had a relation with concept of time similar to the one that Rovelli suggests.
Yeah. I'm not totally sure of this reading. I mean, one of the usual statements that Rovelli does is that space-time actually is itself a physical object, as a main lesson from GR. Most people would actually agree with that, although maybe you can distinguish slightly different interpretation of the words. But so in this sense, nobody would say, he would not say, I think, that space is a relational property of other physical objects. It's just one of the physical objects in the theory. It's just that it's dynamical as it is in GR. It's one of the dynamical physical objects of the theory.
Yeah. Is that different than that? Space is nothing more than a relational property.
It's not a relational property that other physical objects can have. It's one of the physical objects treated on equal footing as the other ones. It's not a property of physical objects. It's one of them.
Yeah, in that context, I agree. I'm trying to be a bit more general. And these he actually introduces earlier with his account of non-relativistic stuff. So, and he attributes these to Descartes, so maybe the language and the connections are not quite right to formulate very short. So we're just going to put these up. So the ones that will concern us is the time ones. Whatever time measures is nothing more than relational property that physical objects can have. ontological one. The ontology stands for ontological principles. P are just principles, perhaps metaphysical ones. Now, to the partial observables and non-relativistic pendulum. So a couple definitions. A partial observable is a physical quantity to which we can associate a measuring procedure leading to a number. And a complete observable is a quantity whose value or probability distribution can be predicted by the theory. And he exemplifies this many times with its pendulum example, where you have something to measure the elongation of the pendulum. You denote that Q, that's a partial observable, and then you have something to measure the time, a clock, and you denote what you measure that as T. And then you get a complete observable by having sets of these, Q and T. And these sort of form the base of his bid to get rid of forget time. I won't go into detail about that still. Now, so regarding this notion, time is, the T is supposed to be on equal footing with other variables. It's not special. But what does he mean? How do we interpret this slogan to forget about time? So we'll go back to ACA. Now, I wanted to go to the quantum mechanical stuff, but I don't think I have time now. Yeah. So we're just looking at the non-relativistic mechanics. The problems here actually also appear in the quantum mechanical account too, but I won't go into that. So if we apply the conceptual analysis here, we can make this wonderful table. Our table is great. You have the different observable here, so the temporal variable, the position one, and then we have the complete observable there. And we have two things where some sort of temporal relation appears. We'll look at the first one, the one at the top down, just get to the other one. See whether these are problematic temporal relations in this account. Now, T and Q are both just conventionals of the relations among objects, not some background independent parameters. But T here appears to be a measurement of local succession. So we have some sort of temporal relation here, a measurement of local succession of different events. But is our ontological principle violated? Not necessarily, it seems. We could develop this as some sort of relation that is kind of resembles a spatial sort of relation. Like each event is temporally next to another, just as objects can be next to each other spatially at a time. So it seems like in terms of that, they are still on equal footing. So that relation might be okay. And then the other one is dealing with the correlation one. The correlation between these two variables. It seems like to get the correlation, you need another temporal relation of local simultaneity. You know, you have the clock measuring a certain thing when the protractor is measuring something else. Now, does this violate our ontological principle with the T, which was whatever time measures is nothing more than relational property that physical objects can have? Well, it seems like it does violate it. Each event is temporally next to each other, just as objects of time can be temporally next to each other. But it seems that both an instant is still privileged here, in the sense that it's the time at which you have measured stuff. Both partial observables occur at some time. You know, once we catch up with the T, they still have to occur at some time. So it's not clear in this case that the T and the Q are on equal footing regarding the correlations of complete observables. It seems this instant is still privileged here. So whether this can be cashed out in terms of some analog spatial relations that still maintains time as on equal footing is what needs further investigation here. Go on to this. Okay. So,
question?
Okay.
I'm confused. Maybe you could help me out. So it occurs at some time, and that's supposed to be distinguished from occurring at some place. They seem to be equivalent sort of things.
The correlation between, so there's, with the spatial one though, you have some notion of, you have some notion of contiguity there, right? There could be possibly these two events kind of in the same spatial relation, kind of. They're at a particular instant.
And not at a particular place.
Well, so with the temporal, if they're in a particular place, it's kind of defined by the being in a particular instant. So in a way, the temporal thing sort of delineates what space you're looking at.
And maybe the spatial place delineates what location and time you're looking at?
Oh, so they could be. So that's one, I guess that could be one way you can go. So you have this symmetry there between these, the role of the spatial relations defining the temporal ones. I'll have to think about that one.
Right or wrong, I'm just a little bit mixed up myself thinking about this. Do you have anything to clarify that for me?
Well, I was pointing out that there could be some conflict with this ontological principle. But if we go your route and we say the one is kind of mutually informing the other one, there is some kind of relation there that's symmetric with the temporal one and the spatial one, then maybe that's one way you go about developing this so it's consistent.
Yeah.
Yeah. Can I give my conclusion real quick? Because I'm probably out of time. And then I'll answer your question. Okay, so given relations, commitments, and what is a slogan, there is much conceptual cleanup work to be done. I tried to show with what we're supposed to forget about when we forget about time. But there still are some temporal relations. But it seems like the task is we have to show that they somehow mirror or wrap onto or certain spatial relations. So then it could really be said to be on equal footing. And then for our ACA, it does seem applicable to Rovelli's network, but again, maybe you could say I'm cheating, that he depends on some Cartesian principles in the first place, and maybe it's not with other theories, but at least here you can see how it works. And it also appears useful, I think, for schematizing and evaluating his temporal concepts. You can kind of line them all up there and see how they inform each other, and whether there's conflicts, and then you go back and adjust things if necessary. So there you have it. I guess it works. Question that came up.
Yeah, so we have about 5 minutes for questions.
Oh, there's 5 minutes.
We can start.
Yeah, I mean, it might be that you take this example as that you over-interpret this example, because this example, I think, was just taken because for simplicity, and you don't need to take P as really seriously as the time variable and Q as the spatial variable. I think you can just take it as an example. There are two variables, and you try to illustrate the concept of having a relation between these two variables.
Well, the reason I took this case is because it seems to be fundamental in what he thinks he's getting rid of when he says we should forget about time and they're on equal footing.
You could have taken some other example where there's no variable T.
Yeah, with the same number of variables, you could have considered a simple cosmological model with a scalar field and the volume of the universe. So there's no notion of time anywhere. And the theory tells you that only the relation between the two is sensible, and you can then use one of them as your definition of time. Like usually the scalar field as a way to measure the evolution of the scale factor, the volume of the universe.
So I would rather use these examples from drawing any conclusion.
As simple, but at least you're not biased towards the fact that one of the two variables is time.
Yeah, sure.
In this case.
Yeah, but the reason I use this example because Rovelli uses it a lot, and it seems to underpin his account. So that's why I use it.
Yeah, but I'm not sure. I'm not sure he really means it in this way.
But that's the thing. I'm not sure what he means by forgetting about time or equal footing, and that's exactly what I'm trying to use the ACA to analyze. What does he mean by these things? But you might think I'm just,
I mean, this example is perfect to illustrate the notion of partial versus complete observables. But it's not a good example to illustrate the absence of time from the fundamental theory, because one of the two partial observables is a time measurement. So almost by definition, it cannot be a good example for that aspect of the story.
but that's the one he uses.
For partial versus complete observables, then you have to go to a case in which, like cosmology, in which there's no time observable, you take the same relation between two partial observables to define a complete observables, and then you try to reconstruct a notion of time from that.
Yeah.
It's a suggestion to look at that because maybe it's less confusing.
Yeah, sure, but I'm just looking at the one that Rovelli himself actually uses when he's defining these concepts and he's trying to make a distinction. Maybe if he did that. Yeah, sure.
I think what they're trying to drive at is, yes, Rovelli introduces this example, and you're absolutely right about the way you describe how the example functions. In its role of explaining to us the complete versus partial variables. And that's it. That's the role it plays in what Rovelli's doing. Now, there's this other thing to do that Rovelli does elsewhere, which is get rid of time. He does that by appeal to the concept of complete versus partial variables, but not by using the clock example. And of course, even the clock example doesn't have time in it. It just has pointer coincidences, which are just as good as the scalar field anyway, right?
Yeah,
so just the fact that there's a picture of a clock there is not introducing the concept time.
No, I'm not saying it is. I'm just looking at the relations that arise in this account, potential temporal ones. And if we do the ACA thing, we have to look at each part of it and see whether those are consistent. Maybe later on, we could be successful in getting really time completing in these particular relations. This would kind of map out, where those temporal relations will fall out, and if they do, whether they're imported or they're kind of ignored later, whether that's a legitimate move to make as you go along. So this thing just lets you kind of map these out in a way, and if there's a sort of relations amongst each other, whether or already extract them through the different stages of the various quantum gravity programs. So that's what
I have another question from Sam.
I got lucky because it's about this slide. So my question is at the green part in the corner.
Yeah.
So in your account, in your ACA, it wasn't clear to me if we have a conflict, what methodology we use to adjudicate between the different concepts of time. And in fact, that seems to me to be the most difficult and important part.
Yeah.
If we have a conflict, what methodology do we, which one of these do we pick, what considerations weigh out? Do you have anything more to say about that?
I wish I did. Yeah, that seems a very important part, because then you have to, how do we then go back and system?
Yeah, because you can identify a conflict as much as you want, and then it's very easy to adjudicate. You say, I'm going to flip a coin at random and pick one of them, that's the one that went out. But that's not a good methodology, right?
With the principles thing, what I do with the principles is I kind of hold those fixed, so we can't really modify our ontological or metaphysical commitments. They're kind of bedrock. I've done this with Julian Barber's theory. That's what I'm trying to do with Rovelli's theory too. You could go back to the later and question those very principles and ontological commitment you have, see whether those are right. But what I do initially is try to hold those fixed, see if we can have a coherent theory based on that. And if we can't, then we go see what you can fiddle around with.
So in Barber's theory, what's your methodology?
Well, he has a certain... So he has Leibnizian principles underpin his account. And I lay out his scope theory, his theory about time passes. What he says about non-relative mechanics and general theory of quantum mechanics, which is not developed. Since it's not developed, I go towards trying to develop in lines with his Leibnizian networks to make it consistent. The same thing with general relativity, some extensions that could be made that he didn't do, but they would be consistent with that. Then after that, I would try out the concepts of time evolve. We'll see whether there are clashes amongst those. And if there are, then I go back and see the most plausible options or the best fixes for resolving. When they get best, the most plausible, what does that mean? You could say, well, I wish I could say more, but I think it probably varies by case too.
All right. Well, I think we're just about out of time on that. So let's see. Thank you.